So let's go ahead and start. Okay, so today we have a talk by Horacio S. Horacio S. is a professor at IFCA, the Institute of Physics of Cantabria, which is a research institution within the Spanish Research Council and CSIC, and he is also a member of IFISC So Horacio is going to talk today about some energy harvesting. So how you can get some energy out of fluctuation.
Okay. Thank you. Well, I will, in fact, to talk about two aspects that at first sight are not too much related. In the second sight, they are also not too much related. But at the end, I will try to explain how we can connect. Before starting, let me explain to several of you that know me, and why not the rest of the ones that didn't know me. This is a place in the south of Argentina, Bariloche, and over the mountains near the border with Chile. And there is a center, research center, called Centro Atómico Bariloche, where I was working before coming to Spain. Some people ask me, why do you leave such a place? Of course, this building there is not the research center, it's some hotel. Well, I leave it that to come here. And also this building here, it wasn't my house, neither the institute. This is Santander, another part of Spain, the place that Peter just commented. And I left this place to this other place. This is very well known. Okay, you say, well, I was changing, working in nice institutes, came into very beautiful places, but the main reason behind coming here is this, where I am the donkey, and the carrot are these, my grandchildren. So this is the secret. Okay, now, in the last, I don't know, 30, 40 years, there was a change in paradigm, in the sense that what before was a source of problems, noise, the fluctuations, people try to avoid it. Around the 70s, the last century, people started to study the effects of noise, studying what is called noise-induced phenomena. There are a lot of them. Several indicated here. I was working a lot in stochastic resonance, in noise patterns, Brownian motors, etc. And what I will concentrate, will concentrate is in these two aspects together in one hand, and this, the third one, the last one, in the other. So I will discuss noise-induced phase transitions and how they can produce some form of couplet Brownian motors. And in the second part, I will talk about noise as an energy source. This is just to show you what could be the application of this kind of studies. Of course, when we start to study noise-induced phase transitions, we don't have this in mind exactly, but this is a possible application. As you see in the title of this article, the authors speak about noise-assisted reprogrammable non-mechanical logical gates. That means it's a way in which, controlling the fluctuations in the system, you can control the response of a logical gate. I will not come into the details how it is done, but the device is such that the authors explain that here we have a kind of transition, and here another, that can be related with logical gates like NOR or NAND AND. And this is the objective in some sense. in the early 90s, middle 90s, were some studies, even before, some studies on noise-induced transitions. That means system without a spatial extension, without breaking of ergodicity, so there were no phase transitions. And we studied several examples. As a matter of fact, there is a book by Horacio and Lefebvre about this subject. And in the early 90s, people tried to apply study the possibility of obtaining noise-induced phase transitions. But there was some conflict between the needs for a noise-induced transition and the needs for a noise-induced phase transition. The mechanism that was originally discovered around 93, 94, was the one indicated here. A system that, when you consider only one unit, has an instability at the origin. Normally, one can perturb and the system relax again to equilibrium. But in this case, what did this kind of system, it starts to depart and at some moment relaxes and goes to equilibrium again. But this instability is the important aspect. What happens is what is shown here in this series of pictures, just snapshots of a simulation. As you see, one of the previous speakers last week was one of the authors, and another one is in the audience. And the simulation was starting with a very disordered system. As soon as these instabilities start to grow, so produces, let's say, arises, interact with another one and start to grow. And as the time elapses, these form clusters that interact with another clusters and grow and grow and grow until finally they form regions of order states. Like when you simulate the Ising model in 2 dimensions, and with a given adequate dynamics, you see that this is what happens. The systems start to accommodate in the sense of have regions in which the spins are up, regions in which the spins are down, and form this kind of order picture. The model that was used was this one here, discrete model in a particular network, with interactions only to first neighbors. Of course, we can use other kind of interactions. And this kind of functions here, and the multiplicative function related with the potential function, let's say. The order parameter is the mean value of the coordinate, and we need to solve this equation in a self-consistent way in order that we can separate regions in which the system is disordered from regions in which the system is ordered. So it is the most trivial or the most simple way is to use this kind of conditions that is analogous to what one normally studies in a course of statistical physics, the Curie-Weiss method. Mm-hmm. So you can just, sorry? Okay. You can, you have a function that describes the way, an equation like m is proportional, let's say, tangent of m plus eventually the external something that has to do with external field. If this is 0, what we have is a self-consistent equation, and we have 3 possible solutions. In order to find the first possibility in which the three solutions merge in the origin, we need to solve this equation here with this condition. This is at the origin. This is the typical thing in statistical physics. Doing this, what results is this phase diagram. This is essentially noise intensity, and this has to do with interaction. And we can see the continuous line is mean field description. The segmented line is an improved mean field, and simulations more or less represent the same. But what we see is that there is a kind of reentrance. If we start in the disorder region, in which the order parameter is 0, increasing the noise, we can go into the region of order parameter different from 0, and still increasing the noise, we find what is expected, disorder again. There have been several studies, and again with Raúl Toral, we did some studies what happened with the same system if instead of white noise we use colored noise. That means Orton-Uhlenbeck noise, a noise that has an exponentially correlated tail. What happens is the following. This curve 1 corresponds to white noise. Curve 2, 3, 4, etc. corresponds to increasing the correlation time. And what we see is that there is an effect of closing the area in which we can find order. Even more, what we have is, of course, the reentrance we have seen before, but now a reentrance in terms of the coupling. For a given correlation time, we can go from disorder, just changing the order, the interaction, going from disorder to order and to disorder again. What happens is that when the system, the interaction is too strong, the system tends to behave like a deterministic system. And the deterministic system shows no phase transition, no order. Also, reviewing previous results, there was a new mechanism, more similar to what was found for noise-induced transitions, that was introduced in this paper. Again, Raúl was involved. And the idea was to use this kind of description. We have a potential, a kind of mobility here, but introduce noise in such a way that some fluctuation dissipation theorem or relation is fulfilled. Again, white noise. And what happens with this is that we can just write the solution of the stationary solution of the Fokker-Planck associated Fokker-Planck equation with an effective potential that has this form. So this has the form of a Kiswell-Landau. And this term has the typical form of an entropic term. For this reason, it's called an entropic mechanism. The phase diagram that results for this system is from here. This is the mean field description, and this is simulation for system of different sizes, and we have the typical effect of finite size systems. The reason why this happens is that it's shown here. If we have zero noise, what we have is essentially a monostable system. As soon as we turn off the noise, what starts is some interaction, some contribution from the noise that starts a small barrier in the center until the barrier becomes appreciable, and we have a bistable system, and we have transitions from one to the others. Well, in terms of interaction and noise intensity, we have this kind of phase diagram again, in which here we have the order parameter is 0, the velocity is 0, and again here is different from 0, the order parameter, and also the velocity. Another aspect is also very well known. It has to do with the hysteretic, not the hysteric, but the hysteretic behavior. In magnetism, it's well known, this kind of behavior. We have that this hysteretic curve can be walked, let's say, in a clockwise, in an anti-clockwise sense, and this is normal. It's what one normally expects from hysteresis. But in the first case, first model, what was found was the following. One is that very near the transition curve, let's say, we have mobility that is negative. What it means? I apply a field in this direction and the particle moves opposite to it. And an hysteretic behavior that is given here. This is clockwise, just the opposite of the previous one, of the magnetic one. But it's not the only case in physics in which we can find this kind of hysteretic diagram. Also in material science it's possible to find it. The meaning of this hysteresis is just the same as before. Dissipation, energy dissipation. That doesn't change. Well, these people that have found this behavior presented things like it was only possible to find this kind of anomalous behavior, anomalous hysteretic behavior. What is possible to see is that there is this kind of line within the phase diagram in which, in this region, below this line, the system is normal. It's only anomalous in this region. And this is possible to see very clearly if we do what we do before. Include, instead of white noise, introduce correlated noise, orthogonal noise with exponentially correlated. What happens is we introduce this kind of noise. What happens is that this curve, that is the tau equals 0, white noise, start to move to here, to here, and this line moves from here to here to here. This is the dotted line here. But look at this point. This is one of these points. I think it's this one. In this case, it's inside the normal region. But now, with including correlation, what happens is that after the correlation time is increases enough, we find that it is not below but above the curve that indicates the transition from normal to anomalous. And if you look at the behavior with the force and the response of the system, we have the normal hysteretic behavior that as soon as we increase the correlation time, it deforms. Finally, it makes some strange form up to finally reach this anomalous form. So this point that originally was in the normal region enters into the anomalous region. And this point, indicated here as B, that was in the disorder region, here is, for a large enough correlation time, is inside the order region. As a collateral effect, let's say, with another colleague, we study the behavior of the system going to very high interaction constants, and we find that the probability distribution function becomes periodic, and we have a noise-induced limit cycle. It was the first example to be found of this kind of things. Okay, so we have noise-induced phase transition, the possibility of having a current, coupled Brownian motor. What happens with this other mechanism, the Entropic mechanism? We use the same, similar model, let's say, as in the other case, but with this condition. Now we have this effective potential, and what we could expect, according to the studies in this kind of entropic-like mechanism, is that this kind of crossing and this kind of phase diagram. This is noise, this is coupling. In fact, we find this similar phase diagram, but we need to fulfill two conditions, not only one, like here, like before, let's say, like in the previous case in which we study the short time instability. This condition should be fulfilled when the mean field reaches a value m dot, which is a solution, one of the possible solutions of this equation. It has more than one. In fact, if we look at the phase diagram and look at these 3 points, what we find is that when we look at the mean field, at the value of the mean field, in terms of the force, external force applied, what we have is for this, and this point, the black, red, black, red, and blue curves, but I think they are mixed here. It means that we are here in a disordered phase, there is no crossing. Again here, disordered phase because the crossing has disappeared, while the red one, corresponding to this point, has these crossings here. And the relation between the external force and the current has this strange behavior. The stars do not mean to call the attention, but just to hide, let's say, the loop, because these kind of loops that appear here are just an artifact of the mean field approximation. It has no physical meaning. So, for instance, in this point, we can move along this line and up to this point and jump and move. Okay. And if you go in the opposite direction, you move here and jump and continue here. So we have hysteresis. If instead of looking at this point, we look at this constant noise, but varying the coupling, we find something similar. The red corresponds to this point. There is no crossing, so there is no order. But at this point and this point, that correspond to black and blue, both are ordered. And we have this, in this diagram, we have a mixture, mixed the colors. The red one corresponds to this point, and the black one, the red one corresponds to this point, and the blue corresponds to this point. And we see that as soon as we start to introduce into this region the size of the hysteretic diagram increases. What is even more interesting is that it's difficult numerically, but it's possible to make an analytical approximation in the limit in which the coupling is very, very large, because several of the integrals can be approximated. When this is done, what we find is situations like this here, and the hysteretic diagram has this form that is too concentrated around the origin, but has some particular behavior. We see that we find normal behavior if we go in the opposite direction, or this kind of hysteresis, or this other, etc. So going to the very large coupling limit, it's possible to find something like a staircase structure for the hysteretic behavior. This opens the possibility of thinking in, as I show in the one of the first transparencies, that we can maybe think in making a reprogrammable logical gate, changing coupling, noise, etc. Just playing with these parameters. What can be done, or what we are trying to do, is, in one hand, is a detailed description of the phase diagram. That means to make a more detailed analysis in mean field, in one hand, and numerical simulations also of the whole system of stochastic differential equations. To change, of course, the kind of interaction, the kind of potential, and play it a little with these things. But the most important thing, or one of the most important things, is related with relaxation times. Why? If the relaxation time of this kind of system is fast, it's really fast, it means that the system responds very fast. Well, we can just apply a change in one of the parameters and find that we can change the characteristics of the device. But if the relaxation time is too long, the response will be too slow, and except to be a very interesting problem, will not be useful for using it for logical gates. And now let me go to the second part. I think I'm going too fast. The use of noise as a source of energy is not new. Here in Mallorca, you have a lot of examples. The wine mullins, for instance, is using the wind to extract water from deposits. But also, those of you that are not so young maybe remember the clocks, the watch that just charge just with the motion of the arm. This is also a device. Another thing that we can see here is in the sea, the buoy. In the entrance of the harbor, there are buoys with lights that indicate the ship the way to follow in order to arrive safely. Well, in particular in the case of buoys, there is a system. It's not possible or not useful, let's say, to think in a man going with a boat every day and changing the batteries of the light. So we need some system that batteries of long life or some way in which the batteries can be recharged. They have such kind of system, but usually it's a linear system. It's a kind of, let's say, a pendulous, normal pendulous, that with the motion activates some electric system that charges a condensator, and when time arrives, the condensator discharges and turn on and off the lights. But this is not enough, because what we have with linear system is that the spectrum which the linear system responds, the answer of a linear system is just very much concentrated in the resonance frequency of the system. What we need is something that can extract energy from a broader spectrum. And for this, it's necessary to study or to work with no linear source. So the kind of system, typical system, has these components: is the vibrating body, the sea, the void, and the mechanism inside. Some way to store energy that are transduced into a condensator and use the electricity for whatever. These systems are linear and have the problem that I said before. It was, no, I don't know if it was the first, but one of the first groups was in the group of Gamaitoni and Perugia. We start to analyze this kind of system in which we have an inverted pendulum with magnetic pieces here. So this is a bistable system because we have repulsion in this point. So when the pendulum is vertical, it's repelled by the other piece of magnet and goes to one or the other position. The central piece has some piezoelectric material, so with each motion, the piezoelectric produces electricity that is accumulated in some condensator. If you like to see the real experimental device, this is contained in this paper, and this is what they found, a response that for people that work or that knows about stochastic resonance resembles the response of a stochastic resonant system. They have a maximum, but broad maximum. The system is pi-stable, which is typical stochastic resonance. So we can say that this kind of system is just a relative of a stochastic resonance. And it's not an accident. Luca Gamaitoni was one of the many Italians who work in the problem of stochastic resonance. So this is a good question. I don't know the numbers for this. In general, it's not too high, but it's better than nothing. I mean, of course, it's. They say that it's enough to fit some small devices. I know that in some parts they're using not this device because it's not the most practical one, but they use a kind of carpet in a part of a road, highway, and due to the cars go over, presses pieces that has some kind of nonlinear behavior and piezoelectric, etc., that accumulates in some condensator and produce the light that illuminates the road at night. Okay. The question is, in stochastic resonance, the typical example is a system with two wells, bistability, in which the system is driving in one sense or another, and the system jumps from one well to the other, and etc., etc. But there are also systems, monostable systems, non-linear monostable systems that show a behavior of a stochastic resonance. Well, it's possible to find this in this kind of system. Then the answer is yes. And what we have used is the same kind of structure, but instead of having here this potential, this is the potential for the mass, the connection with the condensator, and we have some assumptions like the transductor reacts instantaneously over the oscillator, etc. And the circuit's time constant is very large, etc. So what we change is the potential here from the one associated with the vibration of this pendulum, bistable, to a monostable. This is published here. And the idea was to use this kind of potential. Why? On one hand, it's a very easy potential to handle. And on the other hand, what gives the possibility of larger excursions. What we have here is that the larger the excursion, the larger the oscillation of this pendulum, larger the eventually can enlarge the response of the system. So when we use this form, because it allows very large excursions. And what we found is, this is the correlation time. We use colored noise, as did Gamaitoni and company before. And with changing parameters, we see that for increasing noise, we have an increase in the response, in the accumulated voltage. Changing another parameter, Q is a parameter. What we have used is not exactly Orson-Uhlenbeck noise, but a kind of effective Orson-Uhlenbeck noise that can, changing this Q parameter, can have tails that extends more than in the Orson-Uhlenbeck case. And we see that for larger values of Q, we have an increase in the voltage for different noise intensities. So we have a better response of the system. Again, the possibility, not only the response of the system is large, but can be increased also the capacity of the system. Another question that arises, okay, we have one unit responds in an adequate way, but what we know from stochastic resonance is that the phenomenon can be increased if we have coupled many units. There are limits in which if you couple too much, the response can reduce. But if you couple some units, like a few ones, the response is increased. It happens the same in this case. Well, we have tried with this kind of potential. We don't care about the form of the potential. We just make some study changing the exponential of an oscillator-like potential, and we have the same kind of equation than before, but now coupled to these neighbors. One thing that immediately arises is that there is appears a divergence. Q is the coupling parameter, and if we have a positive value of the Q, the response reduces, while if it becomes negative, it starts to increase until a divergence occurs. What happens is that it seems that it's more convenient to couple the system moving in one direction with another one moving in the opposite direction, a kind of antiferromagnet configuration, antiphase configuration, at least for this kind of coupling. We have analyzed the better exponent, the better exponent here, change the number, sorry, the number of the exponent, we see that small values, 1 or so, are more convenient, so it's what we use. And what we see is that the efficiency can diverge, and if we took just a piecewise, that means n equal 1 piecewise potential. And there is a maximum if we use other values of n. As a compilation, let's say this is the number of units using n equal to 2. And we see that the maximum response occurs when the number of units is 3. Not only for the accumulated voltage, but also for the efficiency. And this is the efficiency for different values of the of this parameter as a function of the coupling. And we see that all of them, after go through 0, diverge. So what is necessary is to think in ways to control these divergences. Of course, this is unphysical in the sense that we can find an increase, but not a divergence. There are possibilities of looking for different forms of coupling. What we have done is to introduce a non-local coupling in the lowest order approximation. That means that it's not only we are not coupling only one unit to the nearest neighbor, but eventually to the following ones. And in the lowest order, we don't find any improvement. One thing that is still pending is to use more realistic potentials. This kind of potentials that are like harmonic ones grow up to infinity. This is completely unrealistic. If we continue applying force, this system will break. So the Wood-Saxon potential seems to be more realistic. Also to consider all the kind of mechanism, of coupling mechanism, and other forms of the system. One of the ways in which we are analyzing and trying to find if there is some improvement is to use maybe harmonic oscillators, but a set of harmonic oscillators, but each one responding in a different frequency, so capturing energy from different parts of the noise spectrum. This is still, we are still performing the simulations and the analysis. And what is the relation between this part and the first part? That one thinks, well, the first part maybe can be related with devices that has a nanoscale size. If they are very small, they would need a small amount of energy, and maybe with this kind of source of energy, if we can produce an adequate device, we can just fit the energy needed by those systems. So this is the final question. And thank you very much for the attention and patience.
Thank you, Horacio. Questions?
I think that in all examples you have in the energy harvesting you will trying to transfer mechanical energy into electrical energy. Can you think in, for example, making use or electromagnetic noise or
Yes,
light noise, something
As
like
a matter
that?
of
Something
fact,
which is not vibrations?
I haven't worked in that, but there are people that is working in such a manner. Yes. Yes, yes, yes. Mm-hmm. Yes.
Other questions? Okay, so if we do not have more questions, we thank Horacio again, and we move on to the hands-on session.
Okay.